Hello, calculus fans. Let's talk about spherical coordinates. This is quite a bit different than the type of coordinate systems you're used to. So the spherical coordinates rho, theta, phi of a point P are shown in the next slide. So these are Greek letters. That's not a P, that's a rho. Rho, theta, and phi. Good news is the theta is the same theta that you're used to, but the rho and the phi are going to be new. All right, here's the picture for spherical coordinates. We got the same angle theta that we've been dealing with. It's the angle between the positive x-axis and the projection of P down into the xy plane. Rho is just the distance from P to the origin, and then phi is the angle that the line segment OP makes with the z-axis. All right, so rho is the distance from the origin to the point. Theta is the same old theta as before. Phi is the angle between the positive z-axis and the line segment OP. Now it's important to note that rho is always going to be non-negative. It's a distance after all. And phi we're only going to measure between 0 and pi. We don't need to measure phi any larger than pi because then we'd come around the circle again, essentially. Spherical coordinates are going to be most useful whenever you have symmetry around the origin, although you don't have to have symmetry. That just leads you in that direction. For example, the sphere with radius c centered at the origin has a very simple equation, rho equals c. This is really simple. The equation theta equals c is a vertical half plane. And then the equation phi equals c is a half cone with the z-axis as the axis of symmetry. Here's a picture of the sphere, the plane, the half cone. Ordinarily, you don't think of this as a half cone. In real life, a cone is, well, what you see is a cone. In math, though, a cone goes both ways. So here's the top half of the cone, and then if c is an angle that's bigger than pi over 2, you can get the bottom half of the cone. So these are two halves of a cone. What we want to do is also find equations that are going to relate x, y, and z in rectangular coordinates with rho, theta, and phi in spherical coordinates. Let's go back to the picture. Now this is the picture that you want. You might want to jot this down because in the next few slides we're going to refer back to this picture. One thing to notice is there's this red triangle. We're going to make use of that triangle. That is a right triangle because the point P is being projected down into the xy plane to the point P prime, and then we join up with the origin to make a right triangle. If you're projecting down into the plane from the point P, then OP prime has to be orthogonal to P prime P. We also create this point Q by taking the point P and projecting it to the z-axis. All right, we take the triangles OPQ and OPP prime, and we get that z is equal to rho cosine phi and r is equal to rho sine phi. Now we already know that x is equal to r cosine theta, and we know that y is equal to r sine theta. Those are the relationships between x, y, and r and theta when we were dealing with cylindrical coordinates. So, in order to convert from spherical to rectangular coordinates, we're going to use these equations. So, we take x equals r cosine theta and replace r with rho sine phi. Same thing with y. We take y equals r sine theta and replace the r with rho sine phi. So now we have x equals rho sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine phi. And then the distance formula gives us an easy way of computing rho. We just have that rho squared is equal to x squared plus y squared plus z squared. Okay, that's all for now.